Hello and welcome back to another episode of Engineering Things. Here today we'll be continuing with a 7th tutorial on PySpice, specifically looking at multiprocessing. Now, multiprocessing is a module in Python which allows us to leverage the multiple processes on a machine. So most computers will have a CPU that will have multiple cores. These days, these cores can go up to 8, 16 or more in some cases, rather than traditionally just the 4 that used to be most common. So what this means is if we have 4 or more cores, we can start to distribute any given task onto all of the cores and then operate those tasks in parallel to greatly speed up the overall piece of code that we're using. Now, there are a couple of drawbacks to multiprocessing in Python. So one of the main, most relevant points here are the different ways in which multiprocessing functions depending on the platform you're on. So if we have Windows or Mac, the way in which these sub-processes are created is using something called spawn. What this means is it actually freshly creates an entire new kind of Python instance for each child that we're producing, for each child process that we're producing. And that's quite a slow thing to do. Whereas on Linux, we can use fork, which is a much faster process where we duplicate the parent, creating an identical copy, and it's much quicker. So basically, if we want to leverage the best performance using multiprocessing, we really want to be using fork, especially if the tasks we're performing tend to be quite short, because otherwise we end up in a situation where the amount of time used to create the sub-process might actually be longer or be not short enough to take full advantage of the process running. If the process running is going to take many minutes, then it might be worth sacrificing a slow startup on Windows and Mac. However, if we're using Linux, we don't have to deal with that problem, and we can just launch straight in. Now, before I switch over to today's tutorial, I just want to highlight the refreshed repository and code which I have produced. Now, recently I've produced a Engineering Things PySpice repository, and I've overhauled the various scripts which you've seen in these tutorial videos so far, and produced a series of notebooks. So, for example, we can go over to tutorial 2. And this then will show the tutorial process that was shown with details. And if you clone this repository and install the Conda environment, you should be able to run these notebooks and get outputs showing you how everything works. So back over to the new repository. I've switched over from using Atom to VS Code. Atom is now depreciated. So we're using VS Code here, and I'm using a Windows for Subsystem Linux environment. We have ngSpice installed, and I have a Conda environment installed, which includes all the various packages we might need. So you can install this environment directly on your own computer. And then the quick structure here is we have all the old scripts that we used in the previous tutorial videos, along with the new one for tutorial 7. And then we now have the updated notebooks as described, where you can run them like so. And then we will get all the outputs showing all the results. So it's a bit more manageable and a bit cleaner to use. So that brings us over to today's work. We're going to be looking at tutorial 7 and parallelization. And I will mention that some of the tools that we use here are defined within utils in these methods sections, which allows us to convert the PySpice formatted sort of waveform output and object into a dictionary with numpy arrays. And this will become clear why we use it later. Now, with parallelization, we are effectively leveraging the multiprocessing package which is provided by default in Python. I will also note that you might have problems getting multiprocessing working directly in a Jupyter notebook, as we have here, if you're not on Linux, so if you're using other platforms such as Windows. So what we want to do is we want to import some of our most commonly used packages, so NumPy and Matplotlib. And then this is an auto reload function, which means that I can reload if I change functions in other files, such as in these methods, that will automatically propagate through. I don't have to restart the notebook. Then we bring in some of our PySpice imports, set up a logger, and then what we do is we want to come down to here. Now I'm actually using the same code as in tutorial 6. Just doing a sinusoidal voltage source with a circuit with a corner frequency. And what I'm going to do is I'm going to loop through the resistor values used in this circuit, and I'm going to actually create several circuits, or actually tens and tens of circuits. And then what I want to do is execute all of them at the same time using multiprocessing. So if we were to do that normally, what we would do is we'd probably either loop through and run each of these circuits independently, or in this case I actually create a sweep. I create lots of these circuits with circuit simulators, and what that means is I can then create a little function to perform the simulation, so actually in this case applying the transient. So now we can loop through, and you'll notice I've placed this loop just on a single line, creating a list. We're going to loop through all of these particular simulations, running the simulations and producing an analysis, and then we're saving that analysis to a list to get this results. So if we do that, I'm going to run all the code up until this point, and we'll see this takes about a second to run. So we've got a tick-tock, just time before, time after subtracting. That takes about a second to run. Now, we want to actually do this as a multiprocessing. So this is actually operating in a loop. We're doing one after another in a sequential way, or also known as serially. So we're doing it one after another. But we want to apply multiprocessing. So we can use a pool here, using with pool, and we're mapping the pool. We're selecting the function we want to use, which is this perform simulation, and we're passing the simulation in. We're performing the transient in the function, and then we're returning the resulting analysis. So you can see here, this is the function we're doing. This is the sweep we are performing. It's all of these simulators. So hopefully this would result in a in a list of results. Unfortunately, when we run it, what we find using this except function is that it fails. And if I didn't use this try except, it would just come up with a bunch of errors. Now we could dive into those errors and try and examine it, but I just want to go through a couple of steps, because if you look at those errors, what you'll find is that one of them is to do with sort of a forking pickler. So we can assume that there's some problem when we're trying to pass these PySpice simulators, or perhaps the PySpice analysis results, into or out of the process, the child process respectively. So we want to go ahead and try something else. So why don't we format the analysis results somehow? So all I'm doing here is I'm using a function I've created on the right hand side in this methods file called format analysis. And as you can see from the description, we extract a dictionary containing SPICE simulation results. So typically these are formulated as waveform analysis results, but we can then cast them to a NumPy array, and that's exactly what we're doing here. So I'm casting it to a NumPy array. So the input is still a PySpice simulator, but the output now is a dictionary, and you can see these typing hints which are sort of helping explain some of that. However, unfortunately, if we run this, it still fails. So even with a formatted output in the form of a dictionary and NumPy arrays, it still fails, and we still get the same kind of forking result, forking pickler error. So why is this happening? Well, why don't we try and actually not pass in the simulator? So what we're going to do is we're going to change what we're doing. We're going to create a function now which takes in a resistance value, and then based on that resistance value, it creates a circuit just as we did before. It creates the simulator as we did before, and then now it actually performs the analysis here within the function and then returns the formatted results, the extracted results, so not the PySpice analysis object. So why don't we do that? What we're going to do is we're going to use the same resistor sweep that we used before, and we're going to run it using this create and perform simulation function. What we find is that does complete. So there is obviously some problem to do with passing the both the PySpice simulator object into a child process and also the analysis PySpice object out of a process. It can't pickle it. The Python cannot pickle it in a way currently, and therefore we actually need to both create, run, and also extract the results out of the analysis all within the process for us to successfully use the multiprocessing module. So now we can compare this directly with the exact same thing, but operated serially. And that takes, again, about a second. So we see that we get sort of a 2.39 times speed up compared when we use multiprocessing. So we're over doubling our performance. And what we would probably find is if we increase that size, so let's change this resistor sweep, and what we would find, we could probably produce a plot of speeds, but what we find is this probably will scale such that as we have bigger and bigger things we want to run that take longer and longer, the performance gain of multiprocessing will increase. Now we also want to make sure that the two simulations from the serial and multiprocessing results are the same. So we can run that and we find that yes, indeed, the results are the same, which makes sense because they are indeed exactly the same. So, as I said in summary, we need to do the circuit creation, simulation, and extract the results all within the subprocess for us to be able to use multiprocessing. We can also now go over to a single script which I've written, which is almost identical to the tutorial Jupyter Notebook, except we've written it as a script. So we get similar results here. This, however, is using the initial slightly restricted sweep of resistors, and what we find is that the speed up is actually significantly larger. So performing multiprocessing in the notebook is actually slower than performing it within a script. So you will be finding by using multiprocessing that we are significantly improving performance, especially with longer simulation times. So thank you very much for watching this episode of PySpice. I hope that you found this helpful, and it really demonstrates how we can start taking this Python code, we can start making efficient parameter sweeps, and then finally we can now scale those parameter sweeps by using multiprocessing to make sure that they are as fast as possible. Thank you very much.